So, one of the things you will come across in this section as well is word problems, which I know is your favorite thing in the world. Now, the word problems for rationals generally come in only 3 forms: percentage problems, distance, rate, time problems, and work or jobs to be done problems. When it comes to our percentage problems, it really comes down to knowing how percentages work. How do you find 20% of something? What do you do? Times it by 0.2. That's something times 0.2 will get you something else. Where this is the whole, and this is that part that you will get. Now, does that look like a rational equation? Does it look like a bunch of fractions? No. Reason being is when we do our percentages by changing them to 0.2, we've actually moved away from having the fraction. 20% is 20 out of 100. Percentages are in themselves fractions out of 100. We just don't tend to use the fraction. We avoid the fraction. And here's the thing, you can continue to avoid the fraction. Just know that when it comes to percentage problems, you take that percentage and essentially you're dividing it by 100. When you changed the 20 into 0.2, that's where 0.2 came from. Move the decimal place twice if you prefer. It's dividing by 100. And you multiply that percentage as a decimal times the whole, and that will give you the part. And then you're going to create equations using that structure. Distance, rate, time problems. I know many of you have taken physics classes. You required some physics in high school. Does anyone remember the relationship between distance, rate, and time? How about this? You're driving down the highway going 50 miles per hour. You travel for 2 hours. How far did you go? 2 hours at 50 miles per hour. You went 100 miles. What'd you do? How'd you get 100? 50 times 2. So, you found the distance was equal to the rate times the time. Or, generally speaking, when it comes to these problems, typically the time is going to be the thing that we really don't know, or we don't know enough about, or we know too much about. Either way, we're generally going to have this set up as distance divided by rate will get you time. And then there's the work and the jobs to be done problem. This one is similar in idea to distance, rate, and time. It doesn't have a generic formula. It's however many jobs you need to get done is going to be equal to the rate it takes you to do it times the time, or the rate at which you do it times the time that you take. Except in this case, generally when you're going to be working with these jobs, rate, and times problems, you are going to be dividing in a slightly different way. It's going to be your rate is equal to the number of jobs that need to be completed divided by the time at which you have done they take. Now these are just the general structure of the internal parts of the equation. And that's going to make a little bit more sense as we get into the problems. But as we get into the problems, you're going to see situations where they tell you a difference between things, where they tell you a total of things, or they tell you that the items are the same. In a math class, what do you do when there's a difference? How do you find a difference? What operation? When there's a difference involved, you're going to have to subtract some things. What do you do when there's a total involved? How do you find a total? You add things up. What do you do when you're told things are the same? They're equal. So you're going to have situations where you're going to have to subtract some things, you're going to have to add some things, or sometimes things are just straight up equal. Okay. So first example that we have, Ray adds an 80% acid solution to 16 ounces of a solution that is 10% acid. How much should she add to create a solution that is 50% acid? Oftentimes these percentage problems are adding things together to create a different resulting percent. First thing you want to do is determine what type of problem it is. I already kind of gave that away. It's a percentage problem. And the percentages on these problems are going to essentially end up in different categories. We're going to talk about the 80% situation. We've got a 10% situation going on. And we are trying to combine them, in other words, add them, to create a 50% situation. Now these are just headings that I'm putting on what I have. You don't have to put the headings, but I found that oftentimes it helps people make sense of things. Okay, so this is the structure of what we're doing. The first thing we should probably do is figure out what our variable is going to be. I personally like to use X, but I need to know what X stands for. In this case, it's an amount of which solution do we not know how much of it there is? Which one is it asking us to solve for? Ray adds an 80% acid solution to 16 ounces of a 10% solution. How much should she add? Which one is she adding? Technically adding these two, but we know how much of that one is, so yes, it's the 80%. So X is the amount of 80% solution. Now earlier, when we talked about percentage problems, we said percent over 100, which is just the percentage as a decimal, if you prefer, times the whole will get you the part that it cares about. In this case, the part that it's telling you about is it's telling you that it's 80% acid solution, so the acid is where that part is coming into play. And you add up to get the acid to balance out to be 50%. So, this right here is going to be the structure that I put under each of these columns. The percent divided by 100, or if you prefer the decimal form, I tend to skip to that, times the whole amount of that individual solution. So starting with the 80%. Would you prefer to write 80 over 100 or just 0.8? That's where I'm at. Times. How much of the 0.8 or of the 80% solution do we actually have? Isn't that our unknown? X plus 10% solution. 10% as a decimal. 0.1. Times how much 10% solution do we have? 16 ounces. So 16 equals 50% solution. 50% as a decimal. 0.5 times the amount of solution that we will have that's 50%. It's not X. X is the amount of 80% solution. We don't want to introduce another variable. But here's the thing, you know this too. Because what if I told you in the end we found out it was 4 ounces of 80% solution that we added? How many ounces would we get as a result in this category? If I added 4 ounces to the 16 ounces? 20. What if it was 10 ounces? of 80. Then all of a sudden I would have had 26. So would you agree with me that the amount of 50% acid is just the amount of these two acids added together? This one's X, this one's 16. What do you get when you add X and 16? 16 plus X, or X plus 16. Which means the amount of this solution we have is the X plus the 16. We have created the percentage equation. Does it look rational? There's no fractions. The percentage ones, we can avoid rationals altogether, which is kind of nice. We just have to solve this. How do I solve an equation like that? Simplify first. What can I simplify? 0.8 times X is just 0.8X. 0.1 times 16 is 1.6. Equals 0.5 times X plus 16, I could distribute 0.5X plus 8. There's decimals involved, but do you know how to solve equations like this? It was a rhetorical question. We all know the answer is yes, and if the answer is not yes, I'm concerned. (0.3x) is equal to 6.4. Divide by 0.3. I get a number. (21.3) repeating. And that is ounces of 80% solution. Now some of y'all are giving me blank stares like I'm crazy right now. We'll come back to the others. Let's skip to question 6. Carter adds a solution that is 15% acid to a 70% acid solution to make a 60% acid solution. How much of the 70% solution should he add to create 54 ounces of 60-ounce solution? Okay, start this off. Think about what the process is actually doing. What are we doing with these solutions? Adding which two? Adding 15 and 70. To create which solution? 60. Figure out just basics of what you're doing. Next thing you should do is figure out what it is you're actually trying to solve for. Define your variable. I like X. X is asking us to find how much of which one? Yeah, it says of the 70% solution. We can then write our equation. Our equations will take the decimal forms of the percentages times their individual amounts. I know I have how much? Well, 70% solution is x, so the 0.7 is getting multiplied by x. What other amount do they give me? Go for it. They tell me that we're trying to get 54 ounces of 60. I don't know on this one. They don't tell me anything about this one, and it's not what I'm trying to solve for. That's the one that's going to end up being parentheses every single time. Is the one they don't tell me anything about, nor am I trying to solve for it. This amount and this amount together needs to make 54. I don't know either of these amounts, but let's say this one that's x, let's say it was 20. How much of that one would there had to have been?
34.
How'd you get it?
Minus 50.
The 54 minus the random number I came up with, 20. If these two have to add together than that, this subtracted from this should get me this amount. Which means this should be 54 minus whatever that amount is. Do we know what that amount is? No. Can I solve this equation at this point? Yes. Am I going to stop for this particular problem right here? Yes. Because for the sake of time, the new thing today is setting up the problems. And we've got two different types of problems we're going to see yet. Are we feeling a little less blank stare at this one now? If not, we're going to have to get more practice when we do the actual assignment, because I don't have more examples of this, and we got to move on from this one. Okay, I said we were coming back. Question 2. Ella is rowing a canoe on a river. In calm water, her rate is 6 miles per hour. It takes her 3 hours to travel 10 miles round trip. If Ella rows at a constant speed, what is the speed of the current? Definitely not a percentage problem. There's not a single percent on there. Is this distance, rate, time, or are we trying to do a job? Distance, rate, time. And I told you, distance, rate, time is going to be time equals distance divided by rate. So, these are essentially my categories in this time. It's going to be times that we know. Ella is rowing on a canoe in calm water. It takes her 3 hours to travel this trip. If the time she rows is constant, what is the speed of the current? Okay, categories for distance, rate, time. Sometimes they can be different things traveling. Sometimes they can be a matter of kind of how you travel. Okay, time is our category. What do we know about time? What was that?
Takes you 3 hours.
3 hours. Is it telling you 3 hours is a difference in time, a total of time, or saying things at the same time? It's a total time, which means I'm going to be adding two things together to equal the total time. The things that I am adding together is the things that take up time. She's traveling down the river. But there is a difference because it's a round trip. When you travel in a round trip, what are you doing? See, a couple people do a version of you're going there and you're going back. Now, when you're traveling down a river, do you go the same speed both directions? No, that's a change, which means we have our time downriver and our time upriver. These are our different setups that we're going to try to do as a distance divided by rate. So these ones actually are going to be rational. Starting with distance. Downriver. What is her distance going downriver? If the total trip is 10 miles round trip, downriver you're going 5, and upriver you're going 5. Those are the distances for both of these. Now I need to do their distances divided by their rates. What do we know about rate? Six miles per hour is her in calm water. Is a river calm water? No. But here's the other thing I know about rate. It asks about the speed. What's the speed of the current? Current does what to you when you're traveling down a river? I heard someone say increase your speed. Is that always true? Is the current always increasing your speed? Depends on what direction you're going. If you're going downriver, is it increasing your speed? Downriver means going with the current. Yes, it's increasing your speed. So if in still waters she's 6 miles per hour and we're increasing it with the current, how do you increase something in math? You add her water, or her speed, plus the water current speeding her up. When you're going against the river, when you're going upriver, what is the current doing to you? Slowing you down. It's taking your speed and decreasing it. How do you decrease in a math class? You minus. So her speed was 6 and she was slowed down by the current. Now, since these are distance divided by rates, these are times. Time downriver, time upriver. What do we know about total time? It's 3. Distance, rate, time problems are created by making these fractions. Guess what? You solve these the same way you did yesterday. For the sake of time, we're stopping on that problem right there. I'm regretting rearranging these problems. We're going to skip over 3 for now. We're going to get to 4. Because 4 is the other distance, rate, time problem. Jared and Andre leave their house at the same time to go to a friend's house. Jared chooses to bike there and Andre chooses to drive. Jared is traveling 20 miles per hour slower than Andre and therefore arrives an hour later. Find the rate of each form of travel if the friend's house is 30 miles away. In a distance, rate, time problem, again, your categories are time. What do we know about time? Talks about time in there. Someone arrives an hour later. Specifically, it says Jared's the one traveling slower, so Jared arrives an hour later. Is that a difference? Is that telling us a total, or is that telling us that they are the same? It's a difference between them. So we're going to have to be doing something minus something to equal something else. Okay? Now, those somethings are times. If Jared arrives an hour later, is Jared's time the bigger one or the smaller one? Bigger. So Jared's time is going to be subtracting the 1 hour to get Andre's time. Because Jared's was the bigger amount of time. So that's the one that gets subtracted from. The setup is distance divided by rate. What distance does Jared travel? 30 miles. That's how far the friend's house is away. Divided by, what do we know about Jared's rate? Jared is 20 miles per hour slower. How do you slow something down in a math class? What do you do to the numbers? Subtract. Wait, so I'm going to subtract 20 from what? From x, where x would then represent Andre's speed. Because I take Andre's speed and slow it down. Okay, how far does Andre travel? Also 30 miles. What do we know about Andre's rate? In other words, his speed. What do we just call it? Not 20x, just x. Then solve. We have one more type of setup that we ought to talk about. It's the easiest of them. The last one's the easiest one. Jobs to get done tends to be the easiest because of the fact that it always sets up the same way and really easy to work with fractions. So in a jobs problem, that's what this one is, because it's talking about completing the raking of leaves. The setup is always jobs divided by time is going to be equal to rate, and so your categories are going to be rates. It took Anthony and Travis 6 hours to rake the leaves. I am reading off screen. At their cabin last year. The year before, it took Travis 10 hours alone. If Anthony rakes the leaves himself, how long will it take? Okay, in the jobs problem, generally what's going to happen is you're going to have this person doing it, and then you're going to have a situation where they do it together. The way that rates work is if you've got two people doing something, in this case, Anthony and Travis, their rates added together will give you the rate of them working together. Now the situation is always jobs divided by time. How many jobs are they trying to complete? One job. Does that matter if it's Anthony, Travis, or them working together? Is it still one job every time? Which means every fraction is 1 divided by. What is Anthony's time if he does it alone? It's what we're trying to solve for. not 10. If Anthony rakes himself, how long will it take? That's the one we don't know. That's X. If Travis does it alone, he takes 10 hours. If they do it together, it takes 6 hours. That's all. Those ones tend to be faster. It's generally always 99.9% of the time they're doing one job, and you just do the one divided by their individual times. Add the two separate together to get the overall together. Okay, I have spoken far long enough. I do have a worksheet for you guys. Remember, coming up on Thursday is a work day. Because I knew that today would be a long day, I also know that tomorrow is going to be a bit of a long day. I wish I could do a work day for each separately, but unfortunately,